finite element method works because we take a whole domain and we carve it up into lots of cells, and we have elements on those cells, and those elements sometimes talk to each other across cells. And the set of all cells is called the mesh, because that's what they look like. And so we need a bit of maths, a little bit of graph theory to describe how meshes work. And so the way we're going to describe this is loosely based on a paper by Anders Log from 2009, which roughly describes how most finite element libraries do this. Log 2009 itself is actually based on something called Nepley 2009, which is the properly mathematically rigorous concept of what a topological mesh looks like. However, that paper is written in the language of category theory and is frankly terrifying. Log 2009 is more or less Nepley 2009 translated into human. It's a lot easier to follow, but actually everything we need to know about this is going to be on this page. So, when we talk about the mesh, you look at the mesh and it looks like a geometric object, and a mesh does have a geometry. But actually, for our purposes, a mesh is primarily a topological object. So we are primarily concerned with what connects to what, and where the bits are is a secondary issue that we get to later. So for current purposes, it's just topology. And the dimension of a mesh, the topological dimension of the mesh, is the largest dimension of all the topological entities in the mesh. And a topological entity is a vertex or an edge or a face or a cell in 3 dimensions. So a thing, in other words. And for our purposes in this course, the topological and geometric dimensions of the mesh will be equal. They don't have to be. So you can have a mesh with a higher geometric dimension than its topological dimension because you are meshing a manifold immersed in a higher dimensional space. So for example, if you have the surface of a sphere and you want to mesh the surface of the sphere, your mesh has a topological dimension of 2 because the highest dimension I'll just rewind slightly and then I'll edit it out of the video. So you can have a mesh which has a higher geometric dimension than its topological dimension, for example, a mesh of a sphere, because then what you're going to have is the highest dimensional objects on the mesh will be triangles, for example, so they're faces, so they're 2-dimensional objects. So that gives you a topological dimension of 2. But it's going to be floating around in 3-dimensional space, so its geometry is going to be expressed in 3-dimensional coordinates. So that's the distinction between topological and geometrical dimension. In our case, we're just going to do 1D meshes in 1D and 2D meshes in 2D. So for purposes of this course, they're going to coincide. Anyone who might be thinking of doing an MRes project in large-scale ocean modeling to randomly think of something might need to think about the case of solving a problem on a sphere. I apologize for the in-joke there. Right, so the other very, very useful concept here is codimension. So it turns out that it's not just useful to think of the dimension of objects, so a vertex is dimension 0, an edge is dimension 1, and so on. It's useful to think of their dimension relative to the full dimension of the space you're in. And that's the codimension. So a codimension 0 object is an object which has the same dimension as the space you're in. So those are the cells. So in 1D, cells are edges. They have dimension 1. The space has dimension 1, so that means they have codimension 0. That makes them cells. In 2D, then the cells have dimension 2, which is the same as the space. Again, it's codimension 0. So that's why codimension is useful. In finite element, as I'm sure you've already observed in Colin's part of the course, what we do all the time is integrate by parts. And when you integrate by parts, you get boundary integrals. So actually, in the finite element method, we're also concerned with what happens on the boundaries of cells. And the those are the spaces of codimension 1, that is, the spaces with one less dimension than the full space. And the terminology that we use for that is a facet. So this is ever so slightly confusing. A face is a dimension 2 object, no matter what space we're in. A facet is a codimension 1 object. So if you're in 3D, faces are facets, because cells have 3 dimensions, facets have 2 dimensions, faces are 2D. But in 2D, faces are cells and facets are edges. And in 1D, cells are edges and facets are vertices. So that's dimension and codimension, and that's how we talk about stuff in a mesh. So armed with that, what you have are cells in a mesh which are polygons or polyhedra of any shape. And remember, at the moment, we're not yet concerned about geometry. So at this stage, we don't have to care whether or not the edges are straight. Don't have to be. We don't care, right? Because they're just connected up. So they're polyhedra of any shape. As a practical matter, almost everyone who does finite element uses either simplices or hypercubes. So simplices are the N triangle, so interval, triangle, tetrahedron. If you're doing relativistic fluid dynamics or something, then a quartet. And the hypercubes are interval, quadrilateral, hexahedron, and so on. Those are the ones that everyone practically uses. And in this course, we're going to do simplices, so triangles. So in 2D, meshes are made of triangles. So they look like that, and now we know why they're called a mesh. And we need a language for talking about meshes and all of the connectedness that happens in a mesh. And so the language that we very often use for this is we number entities, and we number the entities within their dimension class. So that means an entity is basically described by a pair, and the first number in the pair is its dimension, and the second number is its index within the set of all things of that dimension. So here, the vertices are in black, usefully. So the vertices start with the number 0 because they're 0-dimensional, and there's the 0, 0 vertex, and there's the 0, 11 vertex. Similarly, edges start with a 1. So 1, 12, 22, 1, 23. And cells start with a 2, 2, 12. Equivalently faces in this circumstance. So that just gives us a mechanism for talking about them. But you have to come back to this later on, because you will, all the way through all the numbering magic you have to do, constantly have to be thinking about entities as a numbering pair. That will trip you up. So that's the thing that you get out of that. So it's also true on the reference cell. So if you remember, we've been talking about reference cells, and we've saying we've got the reference interval goes from 0 to 1, reference triangle, which is a triangle with vertex at the origin, and then 2 vertices, one x is 1 and one y is 1. And we've talked about the location of their vertices thus far, because that's what we needed. But the reference cells themselves look a little bit like a tiny little mesh with one cell. So the reference cells themselves have their own little topology. And if you remember right back at the beginning, there was a topology associated with the reference cell, and we didn't really pay it very much attention. And the reference cell topologies, there's an animation there which you can watch in your own time. I won't skip to that now. The reference cell topologies are, in the first instance, quite simple, but in the second instance, introduce us to the concept of orientation. And that turns out to be very important. So if you are a reference interval, there are 3 entities. 2 of them are vertices, and 1 of them is an edge. So the 2 vertices have numbers 0, 0, and 0, 1, and the edge has is the 1, 0 entity. You'll notice there's an arrow on the edge. So all entities that are bigger than vertices have an orientation. That matters because when you have multiple nodes on one entity, it matters what order they come in. And in order for there to be a concept of order, you have to have a concept of direction. And if you don't get that right, then what happens when two cells touch in a mesh is that they are likely to disagree on the ordering of the nodes. And then your finite element space doesn't become continuous, it becomes some weird, twisted space which makes no physical sense whatsoever, and you get the wrong answer. So having the orientations correct is important. So the orientation convention that we are going to use is numbering based. So what that means is that this edge orients in this direction because the vertex at this end has a higher number than the vertex at this end. So you orient from lower to higher. When we do this, the reference triangle, more or less same story. So we have three vertices now, they're numbered 0, 1, and 2. We have three edges. Okay, the convention with numbering edges is, on a simplex, is that the edge is numbered by the opposite vertex. So this is the 0 vertex, so that's the 0 edge. This is the 1 vertex, and that's the 1 edge. The reason why that works out on simplices is because when you are the facet of a simplex, the vertices you have are all but one of the vertices in the simplex. And so the unique thing is the vertex you don't have, which is the opposite vertex. So that's why you number it out like that. So that gives you those numberings, and then there's only one triangle in the middle. So these guys, once again, number from low to high. So that means, unlike some people's numberings, the edges don't orient around. These two edges orient into there. So geometrically, that looks a bit weird, but topologically, that makes perfect sense, and it has the effect that if we are ever so slightly careful about how we do our global numbering in a bit next week, that all of the orientation problems fall out and we don't have to write any code to actually deal with orientation. So this is doing the maths right so that we don't have to do the code. If you have a cyclic-based orientation, then you have to have orientation code in your lookups, and it's all really, really messy. Okay, so as I mentioned earlier, what we care about meshes is what's next to what, so adjacency. And so that's the critical thing here, and adjacency is in fact a function. So, and the adjacency function tells you which things of lower dimension than you are next to you. So you can expand your definition of the adjacency function to also go in the other direction. It gets more complicated. And the reason why it gets more complicated is if you've made the assumption that your mesh is composed of cells of exactly one sort of topology, so cells made of triangles, for example, then it's always the case that there's a fixed number of things of dimension lower than you next to you. So a triangle has 3 vertices and 3 edges. A edge has 2 vertices, no matter what. The other way up, it's not true. So if you're a vertex, any number of edges could meet at that vertex. And so that's a much more complicated function. So by only looking down, things are simpler. So the adjacency function then goes from effectively it's actually a 4-way function, but it's a set. The best way to think of this is as a set of functions. So the adjacency function from dimension 1 to dimension 2 of an index I is the set of D2 indices which are adjacent to the entity D1I. So, for example, if we do cells, if we're doing cells, then and we're in 2D, D1 will be 2. And if D2 is 0, then it's the set of vertices adjacent to the cell. And if you set I equal to 0 here, then this is the set of vertices adjacent to the 0 cell. The ordering of this is important. That specifies the orientation, and the ordering that we use, which is an ordering that magically works on simplices and can be demonstrated that also works on quadrilaterals as long as your manifold is orientable. So if you want to solve PDEs on a Mobius strip, you're in trouble. But as long as we're in the same space, it's good. Is these are in ascending order. So that then, in line with our definition of orientation that we just had, means that these come out automatically orientated. And that's true whether we're talking local numbering on the cell topology or global numbering on the mesh topology. And that's the trick that makes the orientation of everything on the local cell magically line up with the orientation of everything on the global cell, so that we don't actually have to write any code to deal with that. That's the stunt there. I just said that. Okay. So now we've run all the way down meshes just talking about them as topological objects. But actually, the mesh geometry does matter, because what do we do on cells? Well, we integrate things over cells, and the value of an integral is very much linked to the size and shape of the domain that you integrate it over. So we do actually, at the end of the day, care what the cell is. So so if we first of all think about the case of elements that actually do have straight edges, so they're actual polygons, which are the only case we're going to implement in this course, then it's sufficient to specify the locations of the vertices. And what that implicitly does is it defines a map from the local coordinates on the reference cell to the global coordinates on that cell, which is given by just linearly interpolating between the vertices of the triangle. Similarly, the same thing on an interval. And that tells you what the change of coordinates is, so that when we come to do integrals, you can change coordinates between one and the other. Actually, if you wanted to have bent elements, for example, because you are solving a problem on the surface of the sphere and you find that it's not accurate enough to represent your sphere as something with a lot of flat facets, and that one's for real. We have discovered that if you want to do finite element models for ocean and atmosphere, it's not good enough if the cells are flat. Then all you need is that the relationship from the reference coordinates to the physical coordinates is not linear. So we have a quadratic or a cubic or a higher relationship. And actually, we've already done the mechanism for that. Because when I said in the linear case that on the physical triangle we're just going to linearly interpolate between the vertices, that's exactly equivalent to saying that my representation of the coordinates on the physical mesh is a piecewise linear finite element. Because that's all the piecewise linear finite element basis functions do. They just interpolate between the vertices. And if you want bent elements, all you have to do is say, I am instead going to represent the coordinate field on the mesh as, for example, a quadratic space. And now, instead of just having the coordinates at all the vertices, I need the coordinates along all the edges, because that tells the edge how to bend. And that all falls out. And we're going to use that later, because when we do the change of coordinates from the physical space back to the reference element, we will use the finite element basis functions to compute what that change of coordinates is. So what we've been doing, what we do in this for about the first 6 weeks of this course, is build up this toolkit of operators on basic entities. And then at the end, we've got this nice box of Lego, and we put them all together, and in a very small number of lines of code, we actually solve differential equations. That's the game we're playing. So, as I mentioned, there was no implementation in this section, so it would take probably 2 to 3 weeks for you guys to sit down and correctly implement mesh classes, and it isn't the main subject of what we're doing, and we don't have time to do it. So you get let off, I did it. There is a mesh class which you need to look at in order to understand where all this information is kept. And as with the elements, so you have the generic concept of a mesh, which might be any number of dimensions and might have any particular shape and geometry. And then we have particular versions, and so we've provided subclasses, which are the unit square mesh and the unit interval mesh, which are the ones we're going to use for actually testing things and solving differential equations. And these guys are meshes, so they are subclasses of mesh, and they're subclasses of mesh which mesh an interval or a quad respectively. And there's a plot mesh script which you can use to look at those guys and see pictures that look sort of like this. You will notice here that I haven't told you how to use it. So for those of you not so familiar with the Unix command line, it's conventional that the -h option to commands is for help. And if you run plot mesh -h, it will print out the instructions for how you run it and use it.